Who is introducing you? Bob invites you probably, right? I don't know if Bob is not. No, I think it's supposed to be here. So I was kind of being out to introduce you. I met you in somebody, I think we met you outside my somewhere international. Yeah, I started in July. Things are coming out. Sure. I hope the Bob will appear, but let me just introduce. Okay, so I think I'm just kind of volunteer to introduce today's speaker. So I'm very glad to have Professor Riccardo Comin from MIT Physics Department here to deliver a talk. Riccardo started his job at MIT 3.5 years ago. I just talked to him, and since then I think there are quite exciting things comes around, especially related with this quantum material project within the CIQ. Probably a way to hear some of the stories. Please.
Thanks, Philip. Well, thanks everybody for being here and for the kind invitation to talk here at Harvard. So I'm a junior faculty at that other place down Mass Ave that you might have heard of. It's a safe joke because I don't see anyone from MIT here today. And what I want to talk about is some explorations of the experimental electronic band structure in a new, relatively new class of materials that are based on this 2D Kagome network, a graphical or an artistic representation of which you see over here. And I'm going to discuss in particular our recent discovery of topological properties of the electronic band structure of this 2D Kagome network. So this is sort of the menu for today, roughly. So I'll do a relatively brief intro on what the Kagome lattice is and what are the analogies with other platforms that you're very familiar with, such as graphene, for instance. And I'll discuss how the Kagome is actually a very interesting platform for for harnessing topological phases at the confluence between electronic topology and magnetism. And then I'll discuss basically three materials. So our explorations of the electronic band structure in three materials that are all based, whose building blocks in all cases is this 2D Kagome network. So the first material is this iron 3 tin 2, where we made our first discovery of massive Dirac fermions in a Kagome system, very analogous to what you have in hexagonal and honeycomb systems, and intrinsic anomalous Hall effect. So that relates to the topology. So looking at the connection between the spectroscopy, the single particle spectroscopy, and the electronic transport, so microscopic and macroscopic transport properties. Then I'll talk about iron tin, which is a close sibling of iron 3 tin 2, They have the same chemical constituents with slightly different structure with different stacking sequence of Kagome planes. And here I'll talk about the coexistence of surface and bulk Dirac fermions, and in general about the finding of a simpler electronic structure we could serve as a better basis for harnessing topological phenomena and topological phases. And then I'll conclude with an unpublished work, which is under review now, on this other compound, cobalt tin, which is the same as iron tin, but with cobalt instead of iron. And here we made the very first discovery of topological flat bands, which people have been looking for in this Kagome system for many years. And we finally were able to determine their presence in this particular system. So all of this work couldn't have been possible if it wasn't for great synergy between many different groups across different institutions. The one that I want to flesh out first, because it's really been the key enabler for all of this research, is our collaboration with a group of Joe Chekelski, and the two people that have really spearheaded all of these developments and discoveries are graduate student Mingo Kang from my group and Linda Ye from Joe's group. You see the four of us here all smiling because this was just after the acceptance of our first paper in Nature last year. So we took this picture in Joe's office, just drawing Kagome on the blackboard in the back. I'm sure you've seen this picture before from Joe's talks here. The ARPES, so the angular resolved photoemission experiments, which really provided us the opportunity to peek into the electronic band structure of the systems. Those were performed at the advanced light source, so at the beamline, two beamlines, beamline 7 and beamline 12, the beamlines of Eli Rothenberg and John Denlinger. Transport measurements to look for signatures of the band structure in quantum oscillations were performed at the National High Magnetic Field Laboratory, and then we have a very important synergy with Harvard on both the characterization of these crystals in the laboratory of David, and also on the DFT front with the collaboration with a group of Team Kaxiris. And in particular, Shang Fang has been doing a really, really extraordinary work in establishing the theoretical basis for the understanding of these Kagome systems. And then on the theory front, we also have we have also been really lucky to have this collaboration with the IFW in Dresden and the group of Jerome van den Brink. Okay, so what is the goal? Why Kagome? So the overarching theme here is that of trying to look for new electronic phenomena at the confluence between topology and magnetism. You've heard this if you've been at one of Joe's talks. This is sort of a major theme of research in his group, and what the contribution that we've been doing to this line of research is that of providing an opportunity to examine these opportunities for harnessing the presence of non-trivial topology in this system by performing electronic structure measurements. Now, what is the ultimate goal? Well, that is to find practical and realizations of all of these topological phases of matter, such as Chern insulators, fractional quantum Hall effect, magnetic vials, semi-metallic physics, and action insulators. And in the explorations of the past, I want to say 2.5 years, we've really convinced ourselves that this family of 3D transition metal-based Kagome compounds is really an excellent platform to discover these new phenomena. So this is the Kagome lattice. It's also called the tri-hexagonal tiling. The name comes from the fact that it's a collection or a tiling of triangles and hexagons. You've seen, so it's a lattice that has some sort of connection to the triangular lattice. In particular, if you place an atom in the middle of the hexagons here, you recover the triangular lattice. And you know that the first thing that comes to mind with triangular lattice is geometrical frustration. And the Kagome lattice indeed has been studied for quite a while now, especially in the context of exotic magnetic ground states such as quantum spin liquids, but has received relatively little attention for what regards the electronic properties. Also, when we focus on magnetism, the one interesting characteristic of this Kagome lattice is that when you construct this based on transition metals, so manganese, iron, or cobalt, or nickel, in these intermetallics here that are based on either tin or germanium, so they're like compounds of 3D transition metals and tin or germanium, then we find different possible magnetic ground states, so different opportunities, again, for combining electronic topology with potentially different spin textures. So, and most importantly, the Kagome lattice, and here you see a representation of this hexagon, sort of the sheriff type shape, with the 3 atoms that form the unit cell in the Kagome lattice. So this lattice, this tiling of the 2D plane has the same point symmetries as graphene. So there is a close connection to the hexagonal lattice. In fact, you can map one onto the other, and you can think of the Kagome lattice as basically an extension of the hexagonal lattice, which you form by adding 1 additional atom in the unit cell. So the hexagonal lattice with this fundamental unit cell here has 2 atoms per unit cell, and if we assume a single band model or single orbital physics, such as is the case in graphene with the p-pi orbitals, then you end up with 2 bands in the band structure. So if we look at the correspondence between real space and momentum space, we see 2 atoms in the unit cell, 2 bands in the band structure, and in particular, one of the defining characteristics of the hexagonal lattice is that you have a linear dispersion, so massless Dirac fermions at the K point, and a Van Hove singularity, so an inflection point at the M point. And this is very well known, and especially here at Harvard, this system has been studied very extensively, and you all understand very well the band structure of this material. Now, the Kagome lattice is the same thing because it has the same point symmetries, and if you construct a single band model, assuming only nearest neighbor hoppings for simplicity of the Kagome lattice, then you have the same 2 bands that you have in graphene, so the electronic structure is exactly the same, but then the 3rd atom brings in something extra to it, brings in a 3rd band, and this 3rd band, most notably, is completely flat, again, in the approximation of nearest neighbor hopping. And therefore, the Kagome lattice is not just an interesting platform to harness topological physics in the spirit of the Kane-Meller model at the K point, so looking at inducing topological band inversion here through opening of a spin orbit induced gap, but it also is potentially an interesting platform to explore phenomena where correlations are important. And the correlation become important because you have an additional excitation, or you have an additional single particle excitation in the band structure, which has